Thank you. My talk is going to be much more simple because it was intended for non-specialists and mainly for postgraduate students. So to understand the content of my talk, it is enough to know a little bit of quantum mechanics. As you can see from the title, I will speak about extremely narrow resonances that can be found very often in various nuclear systems. I will show that a theoretical description of such quantum states is difficult, and I will suggest a way to go around these difficulties. First of all, I would like to introduce the main notions related to quantum resonances. As we all know from classical physics, resonance phenomena appear when we deal with oscillations and waves. And in quantum mechanics, practically everything is described in terms of waves. So it means we should expect to find resonance phenomena much more often in quantum mechanics as compared to classical mechanics. And indeed, we know that many, if not most, of nuclear objects, such as radioactive nuclei, are unstable. In fact, they are examples of quantum resonances. Quantum resonances are also called quasi-stationary or quasi-bound state. If we look at a true bound state, it can live forever. And quantum resonance is such state when particles collide and spend some time together before moving away. And in other words, we can call it delayed scattering process. And that delayed time is what roughly is the lifetime of a quantum resonance. This lifetime is inversely proportional to the quantity gamma, which is called the resonance width. And remember, my talk is about extremely narrow resonances. This means that we consider very small values of gamma, and this corresponds to a very long lifetime of a resonance. The important thing here is that during this delayed collision process, the particles kind of forget the original direction from which they came to this state. And when we describe a resonance state mathematically, this has implications. We'll come to that later, but I can say that at the moment that this implies that in the asymptotic behavior at large distances of the radial wave function, only the outgoing waves should be present, no incoming waves. An energy at which a resonance state can be, a resonance solution of the Schrödinger equation can be found is complex, with where the real part is the kinetic energy of the resonance collision, and imaginary part involves that gamma, the width of a resonance. To understand why this is so, we should recollect the fact that the energy dependence of the wave function is given by this exponential factor. If energy is complex, then we come to this exponential. Actually, it's product of two exponentials with involving real part and imaginary part. And here is imaginary unit. So the density of particles is determined by absolute square of the wave function. So when we do absolute square, that first exponential disappears because we multiply it by complex conjugated exponential. And only imaginary part doubled here remains. For true bound state, the energy is real. It's negative and real. So imaginary part is zero. This means that density of particles does not change with time. It's a stationary state. And for a resonance state, we know that the density of particles should diminish with time according to the radioactive decay law. And it's easy to see that this exponential diminishing factor can be obtained only if the energy is taken like that. So it's a simple explanation of why the energy is complex for a resonance state. In experiments, resonances, quantum resonances are observed as certain irregularities in the energy dependence of the scattering cross-section. In the simplest case, it can be like that. We change the scattering, the collision energy, and around certain energy, the cross-section increases, then decreases. So we have a peak. And the maximum of that peak corresponds to resonance collision energy. And if we measure the spread of this curve at half height, then it is what we call width of the resonance. The name is obvious, the reason why it is called so. And it is denoted usually by the letter gamma. And this curve has Gaussian form, bell shape, and can be parameterized like that. If you observe such resonance, it is called bright linear resonance. But in experiment, you can find not only this simple peak, but also various zigzags in the scattering cross-section. Everything depends on the background scattering phase shift. But anyway, the energy interval where this zigzag takes place characterizes the width of a resonance, and center of that zigzag, the central part middle, corresponds to that resonance energy. Here you can see examples of resonances observed experimentally in the scattering of neutrons by thorium isotope. How can we theoretically determine or predict where the resonance can take place and what is the width of a resonance? I must say that solving a quantum resonance problem is much more difficult as compared to solving bound state problem because of complicated boundary conditions. There are many different methods developed over the years for this purpose. And all of them can be divided in two big categories. One of them is the real energy methods, where all the calculations are done at real energies on the real axis for real collision energies. And the other category of methods combines those where we solve the problem at complex energies. Remember that resonance energy is complex. If we find that complex number, we simultaneously find collision kinetic energy, center of the resonance, and also the width. So this is not a review talk about different methods, so I will not go into details. I only give you a rough idea how, for example, that one of the methods belonging to real energy methods works. So the simplest thing which you can do, you just calculate cross-section at different energies, draw a curve, find its maximum, and it corresponds to a real part of the energy. Then you measure the spread of the curve, and you find gamma. Or alternatively, you can calculate the scattering phase shift, and it can be shown that around resonance, the scattering phase shift changes in pi. So you draw the curve, and then you measure the interval on which that change in pi takes place. There are many others, much more sophisticated methods, but all of them are based on the same idea. You find certain irregularities in behavior, this or that parameter, and measure the energy interval on which that irregularity takes place. And remember, again, I'm coming back to my title of my talk. It's about extremely narrow resonance. If we try to use that simple method for extremely narrow resonance, then it will not work, because that bell-shaped curve becomes like a delta function. And this jump in pi becomes vertical. You cannot measure the interval which this happens. So among the real energy methods, the only one method is able to deal with extremely narrow resonances. This is the old good gamma theory based on WKB approximation. It was suggested by Gamow about 100 years ago to describe alpha decay of radioactive particles. And in this method, the problem is divided in two steps. At the first step, it is assumed that the particle is restricted in its motion by a potential barrier, and potential barrier is considered as impenetrable. Then you find set of bound states within that barrier, and that bound states later at the second step are considered as that resonance energy. And then you let the particle at the second step to tunnel through the barrier. And tunneling probability is calculated like this exponential within, it can be derived within WKB approximation of quantum mechanics. You see, it's easy to calculate for any given potential. You can find this integral. R1 and R2 are classical turning points of the potential. And you can calculate that integral either analytically or numerically with very high accuracy. And then you multiply that penetration probability by the frequency of collisions. You assume that the particle moves inside that potential barrier to and fro between the walls of the barrier. And if we multiply the frequency of attempts by the probability of penetration, you get gamma. But this theory, of course, very simple and in a sense naive, especially when you try to factorize that gamma and to calculate frequency using that classical picture of moving particle within the barrier. And later on, I will show you using two exactly solvable models that the calculation of gamma with the help of this simple approach gives a significant error up to factor of 20. So one should be very cautious when using the gamma theory. And since nothing else is available, people use it to describe decay of various nuclei. So this was about the first group of methods, real energy methods. Now we come to other group, locating asymmetric poles. It's complex energy methods. Each resonance, quantum resonance, corresponds to a singularity, to a pole of the S matrix. To understand why, we should look at the radial part of wave function and consider radial Schrödinger equation. Unfortunately, I didn't put it here. It would be helpful. But I hope you remember that simple radial Schrödinger equation, which involves the potential. So if we go to very large distances, we consider asymptotic behavior of wave function. Then at large distances, potential disappears. And what remains is the Riccati-Bessel equation. It is differential equation of the second order, so it has two independent solutions, which form bases in the space of solutions. As such two independent solutions, we can choose two Riccati-Hankel functions, H minus and H plus. They are actually combinations of Riccati-Bessel and Riccati-Neumann. But the important thing is that H minus asymptotically behaves as incoming radial wave, and H plus behaves as outgoing spherical wave. And this function, which is solution of the Schrödinger equation, radial Schrödinger equation, must be linear combination of that two independent solutions with certain amplitudes, certain coefficients. And that coefficients, of course, depend on the choice of the energy. So they are functions of energy. And these amplitudes are called the Yost functions in quantum mechanics. The superscripts here in and out indicate that they are amplitudes of incoming and outgoing waves. And what is S matrix? S matrix is a certain measure of the difference between incoming and outgoing wave. Like in elementary quantum mechanics, you calculate reflection and transition coefficients. You just make the ratio of different amplitudes. So S matrix is the ratio. Now, remember I told you that during that delayed collision process, the system forgets the direction from where the particles came to this state. And this means that in the asymptotics, you should have only outgoing wave for a resonance state. Because if energy is not equal to resonant energy, then both terms are present. But at the resonance energy, only this term should be present. This can be achieved if we require that F in at that resonance energy is 0. And this is in the denominator. So at each resonance energy on the complex plane, we have points where S-matrix has singularities, the poles. So the procedure for finding resonances looks simple. We need just locate that poles on the complex plane, and for each such a pole, we find simultaneously the collision resonance energy and the width. The question is how to calculate the S-matrix, or how to calculate the Yost function. Here, if we are able to find somehow S-matrix at complex energies, we can locate its poles, or alternatively, we can look for zeros of the Yost function. They correspond to the same points. Again, there are plenty of different approaches how to locate S-matrix poles, but I will not describe these methods. I will just explain how we locate resonances using that equation. So if we find the roots of that equation on the complex plane, we find actually all the resonances. So some time ago in one of, oh, by the way, this is the radial Schrödinger equation, which I didn't put on previous slide. You see if potential at large distances disappears, what remains is Riccati-Bessel equation. So in one of our papers published in 90s, I will give reference at the end. We propose the following way of calculating the Yost function. We look for radial wave function in this special form, where we introduced explicitly in the expression for that function H minus and H plus, and that F capital in and F capital out are unknown functions. They are determined by the choice of the potential. So we substitute that construction into the radial Schrödinger equation, and after some derivations, it's not difficult but long. We arrive to that equivalent system of first order differential equations. So instead of single second order differential equation, we get two first order differential equations for these new unknown functions. And if we compare this form with the asymptotics, you see H minus is multiplied by F in, H plus is multiplied by F out. If we compare it with this, you see that at large distances, that F capital should become F small. So at large distances, they must converge these functions to Yost functions. And for that equations, the boundary conditions are very simple. Both of them are equal to 1/2 at the origin. This is because we require that radial wave function at the origin behaves exactly as Riccati-Bessel function. And if we put here 1/2 and 1/2 and make a sum of them, it gets exactly the Riccati-Bessel function. So the procedure is simple. We take these equations and start at the origin with simple boundary condition, 1/2. And then we numerically solve these differential equations up to the point where potential becomes small or disappear. And after that, we reach the limits. Why? Because on the right-hand side here, where potential disappears, you have 0. So the first derivative is 0 of that function and of that function. It means they become constant. So they reach the limit and they do not change anymore. So we choose the energy, complex energy, solve equations, find these functions for this particular energy. We choose another complex energy, repeat the procedure. Of course, the curves will go differently, and we arrive to different value of the yacht function. And remember to find the resonance. We need to find the zero of that function. So by changing the, of course, not just randomly changing, there is a special procedure how to find the roots of a complex function. We can locate all the resonances for a given potential. This approach works nicely and very accurately for the case of ordinary resonances, not extremely narrow. Then we can find all of them with very high accuracy. We did calculations for model potentials and could easily reach accuracy of 10 to the minus 12 or even better, which cannot be achieved by any other method. But anyway, when you do calculations, you locate the complex point, imaginary axis, real axis. And there is certain error within which that point is located. And remember that we are looking for extremely narrow resonance. And width of a resonance is a distance from real axis to that point. So if resonance is extremely narrow, this point is very close to the real axis. And actually, it might happen that the circle crosses the real axis. So the real part is determined with that accuracy. It is enough. Say our accuracy 10 to the minus 14. For the real part, it's good accuracy. But what about gamma? Gamma is completely lost here if it is smaller than that accuracy. For example, is 10 to the minus 20. And the accuracy which you found is 10 to the minus 14. It's completely lost within that circle. You might think that this is something abstract and never happened in reality, but look at this example. The isotope 238 of uranium can be viewed as a quasi-bound state of alpha particle and thorium core with the lifetime greater than 4 billion years, which corresponds to gamma 10 to the minus 39 MeV. And the real part of the energy, which is Q value, the energy which is released during the decay, is roughly 4 MeV. So this is exactly that case when the real part is many orders of magnitude greater than imaginary part. So in this case, this method fails. So what to do? Of course, you can use gamma theory, but as I mentioned, it is not accurate. So let's have a look at that point with the magnifying glass, which is here on the right-hand side. This E0, it's the point which we roughly determined here, point on the real axis. And about the gamma, we only know that it is very small. And the actual point, complex point, which we want to find, is somewhere here, not far from that point, because it's within that small circle. So we need to find that point, which is the root of that equation. Let's expand the Yost function in Taylor series around the point E0, which is on the real axis. And here is the Taylor expansion, where dot over the symbol means the derivative with respect to energy. Since this red line is very small, the distance is very small, it's in the brackets here, that distance. We can ignore all the higher terms beyond the linear one. Then we look for a solution of that equation. So we equalize that two terms to 0. And from here, we immediately find what should be that actual resonance point. So it is E0 shifted by that ratio. It is a complex number because both of that functions are complex. And then if we find that ratio, then we find the small correction to the real part, but usually it can be ignored because this is large value and this is extremely small. But the imaginary part of that shift gives us gamma. This is what we want to find. But you see here, we know how to calculate the Yost function itself for that point. What about the derivative? To find this, we use the following trick. In one of our previous papers, I will give reference later, we proved that the Yost function in general has the following analytic structure. Here, most of the functions are known functions, known analytically. For example, sigma is Coulomb phase shift. There is expression for it. C is Coulomb barrier factor. There is also expression for it. I do not put it here. It's not necessary. And H, which is here, is just combination of gamma function. It's not the width at the mathematical gamma function, and its derivative. And the only unknown functions here are that A and B, which are all the other factors are always the same for any potential. And these A and B are determined by the choice of potential. I must emphasize that this is exact formula valid for any potential, and it's kind of semi-analytic representation of the Yost function. And for that A and B, we obtained, they are limiting values of certain functions for which we obtain differential equations. I do not put them here just to make things more simple. And again, I simplify the formula further just to make it readable. In actual calculations, we use that full formula. But to understand the idea, it is sufficient to consider neutral particles. In this case, Sommerfeld parameter is 0, C becomes 1, sigma is 0, H times eta also becomes 0. And you arrive from that formula to this simple representation of the Yost function for neutral particles. Now what we need, remember, we wanted to calculate the derivative of the Yost function. So we differentiate that formula. It will involve three terms: derivatives of A and B, and energy derivative of K, which is easy to calculate. Now, to find that derivatives, we expand again in Taylor series. Now these unknown functions A and B with certain expansion coefficients. And again, in one of our papers, we derived differential equations for determining that expansion coefficients. They are actually limiting values of certain R-dependent functions which obey a system of differential equations. It's infinite system and changes from zero to infinity. And they involve expansion coefficients, Taylor expansion coefficients of Riccati-Bessel and Riccati-Neumann functions. To find, say, first derivative at E0, we need, if we differentiate, the constant term disappear, the linear term becomes constant, and if we put E equal to 0, all the other terms disappear. So actually, the first derivative is equal to A1. And the same with B function. So we all actually only need these four coefficients. And for that, we need to solve only the first four equations. And look at that condition. Not all of, it's an infinite system. Not all of them are connected. The first four equations are connected to each other, and the rest are connected to them, but these first four are independent of the rest. So we ignore the rest of the system and solve the first four equations of that system. Again, the boundary conditions are very simple, and the approach is the same as I showed you for the Yost function. We start from 0 at simple boundary conditions and move to large values of R until we reach the point where potential disappears, derivatives become 0, and we reach that limit. This is the procedure how to find that derivatives, and it means we find derivative of the Yost function, substitute it here, and we finally find resonance energy. To demonstrate how it works, only 2 slides remain. To demonstrate how it works, we considered 2 exactly solvable models. The first model is very simple. It's spherically symmetric potential rectangular potential barrier. For such a potential, the problem for the Yost function can be solved analytically. You can find analytic expression for the Yost function, and you can find its zeros, and it's a basis benchmark for comparison for different calculations. To make the gamma small, we let the right-hand side of that barrier moving to the right, the barrier becomes very thick and penetration probability is very small. And in this way, by varying that R2, we can change the gamma from large values to small. So on this graph, when we move from left to right, we're increasing R2, and the gamma, you see here, logarithmic scale, the gamma becomes smaller and smaller. And because of logarithmic scale, the dependency becomes linear here. the solid line is the result of the exact calculation using the analytic expression of the Yost function. And round dots are results of the direct search of the resonance. It means we calculate the Yost function and locate it on the complex plane, and moving to the right, that point moves up, as I showed you, and approaches the real axis. When it is approaching the real axis, the accuracy is lost, and finally the calculations go completely astray. That is produces the wrong result. Below the exact curve, the square dots are results of the gamma calculations. You see, they are always below the exact value. And I calculated the ratio of the exact and the gamma width. It's 2.2 in this particular case. So you see, even with this simple problem, the gamma theory gives the error a factor of 2. What about our Taylor expansion, which I spoke on the previous slide? In fact, it coincides with the exact line everywhere. It is indistinguishable. So that approach is an alternative to gamma theory, and it gives, in this particular case at least, the exact values of the resonance width. Another example, which can also be solved analytically, we can find analytic expression for the Yost function, is the combination of spherically symmetric square well and the Coulomb tail outside. To make, in this case, gamma small, we pull down the bottom of the square well, and the resonance energy is also moving down. In this case, the particle, when it's at very low position, the particle needs to penetrate through very thick barrier, and gamma also becomes small. And here, the curve, similar to the previous one, the solid line is the result of the exact calculations. The round dots are those when we locate resonance points directly by looking for zeros of the Yost function. You see again, and sorry, on the horizontal line is the Q value. So it's the distance from 0 to that dashed line. So when it goes down, it means we move from right to left to smaller values of that kinetic energy. And of course, the gamma goes down also. It's again logarithmic scale. And below the exact curve here are square dots, which represent what gamma theory produces. Again, it's below the exact value. And here you may think that the accuracy of gamma theory increases, but it's wrong because it's logarithmic scale. If you calculate the ratio of the exact and the gamma width, you will see that the difference increases when gamma becomes small, up to factor of 20. So again, it indicates that using gamma theory to extremely narrow resonances is questionable. Actually, this is it, and my summary. I demonstrated that for extremely narrow resonances, it is difficult to calculate accurately gamma. And this can be done using the Yost function by expanding it around that point on the real axis. And for that, you need Yost function and its first derivative with respect to energy. Both of them can be found using the system of differential equations. I promised you the reference, and all the differential equations and that analytic structure of the Yost function can be found in this book, which I recently published in 2022. And if anybody is interested in original papers, in this book, the reference to that original papers are also given. That's it. Thank you.
Yeah, thank you very much for the nice talk. Are there some quick questions for the speaker here?
Thanks for the presentation. I wonder whether it's necessary to actually go to that Taylor expansion. If you go back to these first order differential equations for capital F, okay, there we go, the one with the brace on the left-hand side. So if you simply took the energy derivative of these two equations, you would immediately get a differential equation for F dot, and coupled to F, of course. So you would immediately get a differential equation for F dot, and there's no need to actually carry out any type of Taylor expansion.
It's a good idea. I never thought about it. Thank you.
Okay. Okay, another question is, can you make sure that you will find all resonances?
Of course, the number of resonance is infinite. You cannot find all of them.
But let's say in a certain energy interval.
You draw maybe, yeah. You just draw a square within which you want to find the resonances which are interested for you. And the simplest way is just to scan that square and choosing I usually use Newton method to locate zero of the complex function. And depending on the starting point for Newton method, you converge to this or that zero. The simplest way to find all the zeros within a square, you just make a square and subdivide it in smaller cells. And you just start from the center of each cell, and finally you go through all the cells. With computer, it can be done automatically and very quickly.
I was thinking, for example.
And you sometimes you find twice the same or three times the same resonance, but finally you analyze them and exclude repetition, and you find all the.
I was thinking in terms of the bound states. There you have Levinson's theorem that tells you how many bound states you should find.
Here also, by the way, in my book that I showed, there is a generalized Levinson theory, which includes the resonances within a certain domain of the complex plane. You simply modify the, in Levinson theory, you use the contour of integration, which encloses the states. If you make a complex rotation of that contour, you can include resonances which will be part of that Levinson theory.
Thank you.
If there are no other urgent questions, thank you very much, Sergei. Thank you very much to all the 3 speakers and a half, also the online speaker of this afternoon. And there should